Right. Welcome all. Today's topic is derive the expression for efficiency of class A power amplifier. In the slide you can see that's above circuit, but in the previous class we have discussed about the power amplifiers. Right? Introduction of power amplifiers, difference between voltage and power amplifiers, and need for power amplifiers, classification of power amplifiers. After that topic we have gone through the class A power amplifier circuit. Right, now we have to derive the efficiency, because efficiency is the most important term to be considered in the case of power amplifier, where efficiency is defined as collector efficiency neta is equal to output AC power by input DC power. How much DC power is converted into the output AC power, that is the efficiency. For class A it is around 25%. So we need to derive that efficiency calculation. We need to calculate that, and from the derivation also we have got that neta is equal to Vmax minus Vmin into Imax minus Imin by 8 VCC IC into 100. So from those equations we need to calculate this, we need to derive the expression. The efficiency of an amplifier represents the amount of AC power delivered or transferred to the load from the DC source. The overall efficiency of the amplifier circuit is given by neta is equal to Vmax minus Vmin into Imax minus. So the overall efficiency of the amplifier circuit is given by neta is equal to Vmax minus Vmin, Imax minus Imin by 8 VCC IC into 100. For maximum efficiency calculation, assume maximum swings of the output voltage and the output current. The maximum swings are shown in the figure 3.8. See the maximum swing, that means it reaches to the maximum Vmax and Vmin. The difference between Vmax and Vmin should be maximum. Difference between Vmax and Vmin should be highest, and difference between Imax and Imin should be highest. Then the swings are said to be highest, maximum swings. So from the figure we can write Vmax is equal to VCC. See here Vmax, maximum value in the fourth quadrant, Vmax is equal to VCC, and the Vmin is equal to 0. What about Imax? Imax is equal to, what is that, VCC by R L, and it is 2 times of ICQ. See the ICQ is half of the swing, Imin is minimum is 0. So here Vmax is equal to VCC, Vmin is equal to 0, and Imax is equal to 2 ICQ, Imin is equal to 0. Then substitute these values in the above equation 3. Then percentage neta maximum, because we need the maximum efficiency, so we consider the maximum values. Then VCC minus 0 into 2 ICQ minus 0 by 8 VCC ICQ into 100. Further simplifying, it will become 2 VCC ICQ by 8 VCC ICQ into 100. Cancel those VCC ICQ and we'll be left with 2 by 8, that is equal to 1 by 4, that is equal to 0.25 into 100, that means 25%. Thus the maximum efficiency can be obtained from a directly coupled series fed class A amplifier is only 25%. This maximum efficiency is an ideal value. Ideal value means this is the highest achievable efficiency in case of class A power amplifier. Imagine that this is the maximum value, but what about the practical value we get? It will be obviously less than the maximum value, so we will get around 20 or below 20. So the efficiency for class A power amplifier is very low, so we cannot use this value, cannot use this circuit. So for a practical circuit, it is much less than 25% of the order of 10 to 15%, and the efficiency is very poor due to large power dissipation. Why it is very poor? Because of the large power dissipation. Now draw the circuit of class A amplifier with the transformer load. Why the efficiency is low? Because of due to large power dissipation in the RL circuit. In the load resistor circuit, the ICC and VCC and IC values will occur at RL, which leads to the power dissipation. So to reduce this power dissipation and to increase the efficiency and to reach the maximum value of that efficiency, that is 25%, we should replace the resistor load with transformer load. So now moving on to the next topic is class amplifier with transformer load. Introduction. Due to the load resistor RL is directly coupled to the output circuit of amplifier, the overall efficiency of direct coupled class A amplifier does not exceed 25%. Because the current ICQ passes through the resistor RL, there is considerable waste of power and it does not contribute to useful AC power. This problem is solved by using a transformer as a coupling device between the output of transistor and load. So in order to reduce this power dissipation, we should replace the load resistor with transformer. Now the output power delivered to the load will be maximum if the load impedance is equal to the amplifier output impedance. This is impedance matching, concept of impedance matching, and this is a theorem. If you can remember from the subject basic electrical engineering, there is a theorem, maximum power transfer theorem, in which there should be an impedance matching. In audio power amplifier, the load may be a loudspeaker. It's not a loudspeaker, which has impedance in the range of 3 ohm to 15 ohm. Yes, these are the practical values of a loudspeaker, as we have already stated. In a practical 10 watt to 30 watt loudspeaker, the input impedance is around 4 ohms, 5 ohms. So such a low impedance is there for the loudspeaker, and we have highest impedance in the amplifier circuit. So in order to match these impedances, we should use the transformer. But beside this advantage, we have some disadvantage also. As you know already, the circuit will become bulky and costly, expensive. Right, moving on to the next point. The output impedance of the amplifier is of the order of hundreds of few kilo ohms. Therefore, in order to get maximum power output, the load is coupled to the transistor collector circuit by means of a transformer. The high impedance primary of the step down transformer is connected in high impedance collector circuit, and low impedance secondary is connected across the load, generally loudspeaker. Observe this. If we connect the transformer has two windings, that is primary and secondary. So for the impedance matching, the high impedance primary winding is to be connected to the collector circuit, and we should use the step down transformer, and the low impedance secondary is connected across the load, that is the loudspeaker, in order to match the impedance. So that should be the connection. And if you can see the circuit diagram, right, it is a class A power amplifier because we use the power transistor, and the load RL is replaced with transformer load, and the final end load is a loudspeaker. It is a symbol of a loudspeaker. Now figure shows the transformer coupled class A power amplifier. This is also called as single-ended class A power amplifier because single transistor is used for amplification. The values of resistors R1 and R2 are adjusted to give class A operation. The input capacitor Cin couples the signal to the base of the transistor. See the circuit in which we have R1 and R2 RE for biasing and stabilization. So here we need to select the R1 and R2 value such that the circuit will function as a class A mode, and RE is for stabilization, and the Cin is used to couple the input AC signal to the base of the transistor. The Cin blocks any DC component present in the signal and pass only the AC signal for amplification. Because of this, biasing conditions are maintained constant. We know this from the very first lesson of the subject. An emitter bypass capacitor C is connected in parallel with the emitter resistance RE to provide a low reactance path to the amplified AC signal. RE provides bias stabilization. We know all these things. Now moving on to the next point. The function of step down transformer is to match the low impedance load to the high output impedance of the amplifier. The RL is replaced with a transformer load in which the primary has the high impedance which is matched to the output of amplifier circuit, and the secondary is a low impedance winding which is a step down transformer, and this secondary impedance is matched to the output, that is the input impedance of the loudspeaker. This output is matched to the input impedance of the loudspeaker. So that's why the impedance matching will have happened, because high input impedance of this amplifier circuit is matched to the low input impedance of the loudspeaker. High output impedance of the amplifier circuit is matched to the low input impedance of the loudspeaker. So impedance matching using transformer, how it will happen, just go through it. Transformer, we have primary winding N1 with the number of turns more, N2 is a secondary winding which has lesser turns, that's why it is called a step down transformer, and the input voltage V1 and input current I1, and the secondary we have output current I2 and output voltage V2, and the load resistor RL, and the primary windings resistance is RL dash. Consider a transformer as shown in figure which is connected to a load of resistance RL. While analyzing the transformer, it is assumed that the transformer is ideal. In the ideal conditions, there is no loss of current or power, that means leakage current is neglected equal to 0, right? Those losses are all assumed to be 0, and there are no losses in the transformer. Similarly, the winding resistances are assumed to be 0. The winding resistances are assumed to be 0. Now let N1 is the number of turns of primary, N2 is equal to number of turns of secondary, V1 is voltage applied to primary, Vt is voltage on secondary, I1 is primary current, I2 is secondary current. So now the load resistance RL could be calculated from RL is equal to V2 by I2, right? From the basic Ohm's law, R is equal to V by I. Let the reflected load in the primary of the transformer be RL, which is calculated from RL is equal to V1 by I1. Reflected load in the primary of transformer, that is RL is equal to V1 by I1. From basic transformer theory, we can write from the equations 1 and 2, V1 by Vt is equal to N1 by N2. basic transformer theory, N1 by N2 turns ratio is equal to V1 by I2, and I1 by I2 is equal to reverse of turns ratio N2 by N1. So from equation 3 and 4 we can write V1 is equal to N1 by N2 into V2, I1 is equal to N2 by N1 into I2. As you know all those formulas. From the substituting equations 5 and 6 in the equation 2, we have RL dash is equal to RL dash. Actually this is reflected load is RL dash, it's not the RL. RL is equal to RL dash is equal to V1 by I1. So replacing the V1 with N1 by N2 into V2 by I1, that is N2 by N1 into I2. So by mathematical adjustments we will get finally RL dash is equal to N1 by N2 whole square into V2 by I2, where V2 by I2 is called RL from the basic Ohm's law. So RL dash is equal to N1 by N2 whole square into RL, where we consider N1 by N2 as small n, turns ratio. Small n is the turns ratio, n is equal to N1 by N2. So RL dash is equal to n square into RL. Proper selection of turns ratio results maximum power transfer. So we need to consider the n turns ratio for maximum power transfer. With a suitable example we can understand this. For example, if we want to match a 20 ohm speaker load to a power amplifier so that the effective load may be 8 kilo ohm, then the turns ratio should be N1 by N2 whole square, that is called RL dash by RL. RL dash is 8 kilo ohm and RL is the 20, we get 400. That is the turns ratio will be under root of 400, that is equal to 20. If we select the turns ratio properly, then the high impedance of primary and the low impedance of secondary will result in the matching of this low impedance of secondary to the low input impedance of the loudspeaker, right? So the main point is turns ratio should be selected proper and it should be step down transformer. In this way a power amplifier may be matched by taking proper turns ratio in a step down transformer. Note, remember that for a step down transformer the secondary voltage is less than the primary, obviously, right? And high voltage side is always high impedance side, okay? Hence RL dash is always higher than RL for a step down transformer. This is from the typical values and examples we can understand those relations, right? Now moving on to the operation. First see the DC operation. Since the DC resistance of transformer primary winding is small, right? Because the DC resistance is nothing but a winding which is made up of a small wire, conducting wire, which has zero, ideally it has zero impedance, zero resistance, right? But in practical it will be have very low value, that is around 2 ohm or 1 ohm. For DC operation it will act as a short circuit the winding, so that why it is called, it is very small, the resistance is very small. The DC voltage drop across it is negligible. When resistance is negligible, then voltage across is that is equal to V is equal to I into R. Resistance is negligible, so voltage drop also very low, that is negligible. Applying KVL to the collector circuit, we get from the collector circuit VCC minus VCE is equal to 0. VCC minus VCE is equal to, actually from the class A power amplifier with resistive load we have VCE is equal to VCC minus IL into RL, or that is IC into RL. If you can remember from the previous lectures, we have VCE is equal to VCC minus IC into RL, but in this case RL is 0. RL is replaced by primary winding. Because of this DC operation, that will act as a short circuit. RL is negligible, so the drop is negligible, so we get VCE is equal to VCC. We know that the slope of DC load line is tan theta, that is equal to minus 1 by RL. So theta is equal to tan inverse minus 1 by RL dash. Actually RL dash it is. See the curves where we draw the DC load line. Slope is equal to minus 1 by RL dash. Since RL dash is equal to 0 ohms, the slope of the DC load is ideally infinity. If we consider RL dash is equal to 0, then the DC load line slope will be infinity, that is tan theta is equal to infinity or theta is equal to 90 degrees. Thus the DC load line is almost vertical straight line passing through a voltage point on the x-axis, which is VCQ is equal to VCC as shown in the figure. See the vertical line here, DC load line VCC. How we get that? Because y is equal to mx plus c. From the mathematical formula y is equal to mx plus c, what is the y here? That is IC. And what is the x here? VCE. So VCE is equal to x is equal to something, x is equal to something VCC. From the equation number 9 we got VCE is equal to VCC, x is equal to some constant. What is the x is equal to constant? Line, straight line. If we can draw the straight line, x is equal to some value, x is equal to VCC, right? So that is a direct vertical straight line passing through the constant value, that is here in this case it is VCC. So the DC load line here is a vertical straight line. Now the AC operation. When AC signal source is connected to the input of the amplifier, the resistance in the collector circuit is formed by the reflected resistance of load RL, right? When AC signal source is connected to the input of the amplifier, the resistance of the collector circuit is formed by the reflected load resistance, that is RLS. From the RLS formula we have RLS is equal to n square into RL, which is n1 by n2 whole square into RL, right? So the load line corresponding to this resistance is called the AC load line and has a slope of 1 by RL dash, right? 1 by RL dash. Because for the AC operation we have VCE is equal to VCC plus something, that is 1 by RL, that means 1 by RL into IC will get y is equal to mx plus c, something like that. Y is equal to mx plus c we get. So from that equation VCE is equal to VCC minus RL into IC. So we get the slope as minus 1 by RL, sorry, 1 by RL dash. This load line is drawn through the operating point Q. So when an input AC signal is applied, the base current varies sinusoidally, assuming that the non-linear distortion is absent. The nature of the collector current and collector to emitter voltage also varies sinusoidally, as shown in figure C. From the previous lecture you can see the variation is same as the input voltage variation and current variation. As the collector current is the current in the primary winding of the transformer, the varying collector current produces induced voltage in the secondary of the transformer, right? That's how the transformer will work, right? In the primary winding, if we supply the AC signal, variation in the primary winding will produce the induced voltage in the secondary winding. That's how the resultant output amplified signal will pass from the load resistor, that is here in case it is the primary winding, reaches to the secondary winding, which is connected to the input of load speaker. So the advantages: the efficiency of the amplifier is increased from 25% to 50%. This we can see from the derivation of the theta. The load is connected through the transformer, therefore collector power dissipation is less because there is no RL dash, that is DC resistance is 0. The dissipation is also negligible. transformer connected in the collector circuit provides the impedance matching. Thus, any load may be connected across it. The transformer connected in the collector circuit provides the impedance matching. Thus, any load may be connected across it. So, impedance matching will happen. So, any load if we can connect, according to that, the adjustment will happen. We need to select the proper turns ratio. So, the disadvantage is due to transformer, the circuit becomes bulkier and costlier, as we know it already. The circuit is complicated to design and implement. Due to the transformer coupling, the frequency response is poor. You can see from the frequency response of the transformer coupled amplifier where we get a bulge like thing. That means the curve is upwards. We get the resonant frequency where there is a gain will become maximum. So that is a poor frequency response. So that's a disadvantage. Now the expression for efficiency of this transformer coupled class A power amplifier. The generalized expression we have neta is equal PAC by PDC into 100. So using the equation we get Vmax minus V min times as we know this formula. For maximum efficiency, assume maximum swings. Okay, the maximum swings we already shown like this. From the figure, observe the figure, we can write Vmax is equal to 2 VCC. From where we got this? Because of the DC load line. DC load line is a vertical line which is passing through the VCC, and if we extend the AC load line, right, from the Q point, we get it reaches to the 2 VCC. So assuming the voltage swings to be maximum, and as it is a class A power amplifier, we select the Q point such that the conduction angle will be 360 degrees. So VCC is the middle point of this swing. So we get the Vmax as 2 VCC and Vmin as 0, and Imax as 2 ICQ, same as the previous one, and Imin is 0, from which we substitute, we get the neta max as 2 into VCC minus 0 into 2 into ICQ minus 0 by 8 VCC ICQ. We get 4 VCC IC by 8 VCC IC. So from cancelling the equations, we get 4 by 8, that is 1 by 2 is equal to 50%. So the efficiency is increased to 50% from 25%, but it has some disadvantages. Hence, the maximum possible theoretical efficiency in case of transformer coupled class A amplifier is 50%. For practical circuit is about 30 to 50%, which is still much more than the directly coupled amplifier. Here observe, DC load line is passing through this vertical line, that is VCC, and we have selected the Q as VCQ and ICQ. If we extend the AC load line with the slope minus 1 by RL, we get a point on the VCE, that is x-axis, that is the 2 VCC point. From that simple term, we get an extension of 50%, efficiency of 50%. Now moving on to the next topic, class B push-pull amplifier. What do you mean by push-pull amplifier? Pushing and pulling, opposite operation. One has to push and one has to pull, then the resultant will become balance, right? The push-pull amplifier is a power amplifier and is frequently employed in the output stages of electronic circuits. And in some cases we will use the push, and in some cases we will have the pull. Depending on the corresponding facility, we get to use it to the two different actions, which results in the same output. So it is used whenever high output power with high efficiency is required. So high efficiency in the class A, if you use the directly coupled, that is we get maximum efficiency of 25%, that is theoretical, and if you use the transformer coupled, we get a maximum efficiency that is equal to 50%. But if we want the higher efficiency, then we need to move on to the next circuit, that is class B, where we get the high efficiency compared to class A and high output power also. Figure shows the circuit diagram of a push pull amplifier, two identical transistors Q1 and Q2 placed back to back or employed. Both the transistors are operated in class B operation, that is collector current is nearly zero in the absence of the signal. When the input is zero, the collector current is zero. See the circuit diagram. We have two transistors Q1 and Q2 which are NPN transistors. Both are NPN and they are connected to the secondary of a transformer, that is a center tapped transformer. As we know from the center tapped transformer, the voltage across the secondary is divided as same. The upper portion is also the upper portion voltage will be equal to the lower portion of the secondary voltage. And we have VCC which is connected to the again center tapped transformer connected across the load, that is RL is replaced with the center tapped transformer, and again the output load speaker is derived by the secondary of transformer. The circuit consists of two center tapped transformers, that is T1 and T2. The transformer T1 is an input transformer and is called phase splitter. It will split the phase, that means 180 degrees of one phase and another 180 degrees of the phase of input signal. It is required to produce two signal voltages which are 180 degrees out of phase with each other. The two signal voltages which opposite polarity drive the input of transistors Q1 and Q2. See, this is the very important point here. The transformer T1 is a center tapped transformer which will split the phase of the input signal which are 180 degrees out of phase, which will drive the two different transistors Q1 and Q2. The transformer T2 is an output transformer and is required to couple the AC output signal from the collector to the load. The T2 is an output transformer and is required to couple the AC output signal from the collector to load. T2 is not a, yes, T2 is also center tapped. Okay. Working when no signal is applied with zero input signal. When no signal is applied, both the transistors are in cutoff, because when there is no signal, the transformer's output, that is across the secondary, we have zero output, which will drive the which are applied to the bases of the transistors Q1 and Q2. Right? When there is no input, the transistors will be in cutoff stage, that is output is zero. Hence no current is drawn from the supply VCC. Thus there is no power wasted on standby, and the power dissipation in both the transistors is practically zero. So whenever we don't apply any AC signal, input signal, the output is zero and the power dissipation through that load is also zero when signal is applied. So during the positive half cycle of the input signal, the base of transistor Q1 is positive and the Q2 is negative. Please be careful here, because as T1 is a center tapped transformer, it will divide the input phase of the signal into two 180 degrees out of phase signals, which will drive the Q1 and Q2. If we consider during the positive half cycle, the base of the transistor Q1 is positive and the Q2 is negative. As a result, Q1 conducts and the transistor Q2 is off. When the input signal is negative, Q1 turns off and Q2 conducts. Thus, at any instant, only one transistor in the circuit is conducting. In other words, each transistor handles one half of the input signal. See, whenever at any instant of time, only one transistor is conducting and they are handling only the half of the input only. So they are conducting actually only the half of the input. Thus the output transformer joins these two halves and produces a full sine wave in the load. It has been found that joining of outputs of two transistors is never perfect, and hence the output is distorted. The class B push-pull amplifier is known as double-ended class B amplifier. So the transistors are conducting only during the half cycles. It is only up to 180 degrees. That is, conduction angle is 180 degrees. That's why we classified based on this conduction angle. But at the output, though, because we use the two transistors T1 and T2, and both are conducting only the 180 degrees angle. Conduction angle is 180 degrees, but the output is joining. So there is no wastage of power. Wastage of input is 0. We are getting the perfect output, but the transistors are conducting only the half of the inputs separately and joining them. So we get wastage over 0 and the efficiency is higher. We get the efficiency from the derivation. No need to bother about it now. So now we have to derive the efficiency, right? DC power input. Each transistor output is in the form of half rectified waveform. Hence, if Im is the peak value, so these first see the load lines and the graphs where we get only half cycles or the outputs of each transistors. We get the DC light line as vertical because we use the transformer load, obviously, right? And the AC load line with the slope minus 1 by RL dash, same. And but the Q point here is VCC comma 0. Q point here is VCC comma 0. There is no ICQ because DC current is 0. DC collector current is 0. So the point is Q is in the VCC comma 0 itself. There in the transformer couple, though there is an IC collector current, but it cannot pass through the RL because their load resistance is primary winding, which is a short circuit, which will act as a short circuit for the DC conditions. But in this class B push-pull amplifier, we have 0 collector current for the DC conditions because both the transformers are applied. Input itself isolating the DC conditions. So we get each transistor output is in the form of half rectified waveform. Hence, if Im is the peak value of the output current of each transistor, the DC or average value is Im by pi due to half rectified waveform. The two currents drawn by the two transistors from the DC supply are in the same direction. That's why they added up. See this, the two currents drawn by the two transistors from the DC supply are in the same direction. Hence the total DC or average current drawn from the supply is the algebraic sum of the individual average currents drawn by each transistor. We get IDC is equal to Im by pi plus Im by pi. We get 2 Im by pi. The total DC power input is given by VCC into IDC. That is equal to 2 by pi VCC Im, and the AC power output is, as Vm and Im are the peak values of the output voltage and the output current respectively. See, Im and here Imax is Im and Vmax is Vm. So RMS for the AC we need to consider the RMS value. So Vrms is equal to Vm by root 2, Irms is equal to Im by root 2. Hence the AC power output is expressed as Vrms into Irms, that is equal to Vm by root 2 into Im by root 2. So we get PAC is equal to Vm into Im by 2. Efficiency PAC by PDC. So percentage neta is equal to Vm Im by 2 by PDC, that is equal to 2 by pi VCC Im. So we'll get Im Vm cancels, and from the mathematical adjustments we get pi by 4 to Vm by VCC into 100%. 100. From the equation it is clear that as the peak value of the collector voltage is Vm increases, the efficiency increases because VCC is constant, right? VCC is the supply voltage, so we cannot increase more than certain limit. But for the Vm, that is the input signal, we can increase. The maximum value of Vm possible is equal to the VCC, as shown in figure 1.21c. So the maximum value will become Vm. From the graph itself we can see Vm, where is the maximum value, that is the VCC, the swing. So pi by 4 into VCC by VCC into 100, that is equal to VCC will cancel and we get pi by 4, which is 78.5%. Pi by 4 into 100, 3.14 by 4, we get 78.5 in 0.78.5, 0.785 into 100, we get 78.5. Thus the maximum theoretical efficiency in case of class B push-pull amplifier is 78.5%, which is much higher than the transformer coupled class A amplifier, which is a 50%. So for practical circuit is up to 65 to 70%. So the efficiency is increased much. And this is the Vm maximum value which is possible. Vm is equal to VCC, maximum output voltage. Advantage of push-pull power amplifier. So the efficiency is much higher than the class A amplification. Of course, from the derivation of neta, we have seen the increase in the efficiency. When there is no input signal, the power dissipation is 0. As the DC current components flow in opposite direction through the primary winding, there is no possibility of DC saturation of the core. Ripples present in supply voltage also get eliminated. Due to the transformer, impedance matching is also possible. Disadvantage: two center tap transformers are necessary. Transformers make the circuit bulky and hence costlier. Frequency response is poor. So these are the today's topics. Just quickly go through what we have learned today. First, we have seen the derivation of expression of the efficiency of the class A power amplifier, which is directly coupled in the previous lesson, which we have learned. The derivation we have seen here, eta is equal to V max minus V min into I max minus I min by 2 VCC IC into 100. From where, sorry, 8 VCC into ICC to 100. From where we get this V max and V min? From the graph itself. DC load line and AC load line graph, where we draw the load lines from the KVL equations of the circuits, and we get the maximum voltage swings, and we substitute those values, we get the neta max as 25%, which is a very low, and this is also theoretical ideal value. The practical value we get very less than the 25%. So we need to, in order to increase the efficiency, we go for the transformer load and also for the impedance matching also, and to decrease the power dissipation. When we connect the transformer load to the class A amplifier, the efficiency is increased to 50%. From the derivation of the neta and the concept of impedance matching, the turns ratio is important to be considered here, important point here. DC operation we have seen, DC load line is a vertical line, and the slope of AC load line is minus 1 by RL dash, and n is equal to n1 by n2 into n1 by n2. It is a turns ratio, and we have seen the advantage, disadvantage, and we have derived the expression for the neta in case of transformer load. That will get, we get neta max is equal to 50%, which is a considerable increase from the class A directly coupled amplifier, but which is still a very low value because 50% is wasted. And to decrease that power dissipation and to increase the efficiency to maximum value, we go for the class B push-pull amplifier. First we should know about the push-pull concept. One is active during the positive off cycle and the and in the negative half cycle another transistor is active. Two transistors are there in this push pull amplifier, and we use the center tap transformer, which is very very important in this case. Center tapping means in the secondary winding, exactly at the center of the winding turns, there is a connection will be there, right? Why we have used this center tap transformer? Because it will split the input AC signal into two 180 degrees out of phase signals, which will drive the two transistors which are same configuration, that is NPN and NPN, right? So in this because of this concept and the outputs IC1 and IC2 which are in the same direction, we get the maximum outputs. So we have analyzed this transformer, center tap transformer, couple push pull class B amplifier, power amplifier, right? When the no signal is applied, and when the signal is also applied, and we have derived the efficiency, and that we got beta is equal to maximum beta is equal to 78.5%, which is very very higher compared to the class A. So, and we have seen the advantage, and we can see the next concept, complementary symmetric pull amplifier, from the coming classes. So if you have any doubts, please mail me at suresh suresh akul akul 2001 2001 @gmail.com. If you want to refer the more concept for this topic, please refer the standard books, electronic device and circuits by Berman and Hackins, and also different publishers also available. Please do practice the MCQs and interview questions for your knowledge. And if you want to do experiments, go to the virtual labs. Thank you, one and all. Now I am closing the session, right?